array theory, all right? So we'll have time to go through. In this part, I'm just going to suggest this to you. It's in the book. A lot of what I'm going to have to do is working towards the final form of the actual solution of the equations. And it just might be better if you looked in the book and took minimal notes. So I'll give you a reference. I'm just trying to be honest with you. If I was in your position, this is what I would do. If I was going to learn it. So array theory is just using multiple elements to increase the effective focusing power or gain of an antenna. That's what it really does. Then it uses constructive and destructive interference. And I'm looking for a page. He does it a little differently. He starts with just 2 elements. I'm going to suggest that you go to page 473 where he has this n-element array. And he's talking about how to get the pattern from that. Now, it's not done in a way you'll see it in a lot of books or the internet. It's minimal in his. I'm going to try to give you all the necessary points to try to develop this. And try to appreciate this. It's in his book. The final form of the equation is the one you want. But you need to see how you get there, okay? So I wouldn't ask you to develop it, but I'd ask you to understand how to get this. So with array theory, the best way to do it is we're going to start with a single element, and we're just going to assume from that element that we have an electric field that's isotropic. Even though this doesn't exist, for theoretical purposes, it's fine. This little element will have a current I naught. It'll have some phase, possibly, e to the j. I'll call it phi. And at any distance r away, there'll be an electric field. Now, we know an electric field has polarization. For the purposes of what we're doing with the arrays, we're going to assume everything's polarized in the same direction, so it doesn't matter. But I'm going to say there's an electric field from here, some electric field, and that electric field from the element is given as simply some k over r. You notice that all electric fields that you looked at, the far field is always some constant divided by r. You all with me? And power is some constant over r squared. Y'all follow me on that, class? Power always falls off as 1 over r squared, and the electric field is 1 over r and h field. And I'm just going to say this is in, I don't know, a theta, but it really doesn't matter. And matter of fact, let me do this. Instead of putting k, let me just make this I naught right here, e to the j theta. That way I can make the arbitrary constant that. Now I know it's fictitious, just work with me. So with that in mind, the next step is to build an array, and we have to have some constraints on this. The first constraint is, when I say array, it's just multi-elements. All these antennas are going to be in a straight line. Follow me on that? You've seen arrays like this. Second thing, they'll have the same spacing between them, okay? So I'm not going to show you all of them, but I'm going to go down, I'll show you a line, 2, 3, and then what we can do, this is the way they do it in a lot of books, they'll break it here and say this is the nth one. This is 1 through n antennas. Do you all follow me on this? Now each one of those antennas, now I've got to put some more constraints. I'm going to make the current the same magnitude, and there'll just be a progressive phase shift. So this one will have, as a matter of fact, let me do this. Each one will have a spacing d between them. I have to, if I don't do this, then honestly, the form of the solution is ridiculous. You have to constrain things if you want to have something meaningful that you can actually look at and glean properties from. So now I have that. I have n elements. Each one of these has the same current magnitude, but the phase will be progressively different. Let me show you. I'm going to make the first one just to have I naught. Next one's going to have a phase of I naught e to the j phi. Next one is I naught e to the j 2 phi. Goes all the way down to I naught e to the j. In this sense, there's n elements. This would be what? It would be n minus 1, right? Phi. Y'all with me? So it's a progressive phase shift, where if the first one's 30 degrees, next one's 60, next one 90, and so forth. Y'all with me? Now that phase, I'm going to tell you right now, can be electronically adjusted, just so you know that. It doesn't have to be, I mean, this thing right here, if you have progressive phase shift, it's very easy in electronics to change the phase on these things. And we're going to see in a second, that changes the direction of the maiden beam, or steers the beam. How many have heard of array theory or seen this before? Anybody? It's used in radio astronomy. It's used in a lot of things. Radio astronomy is based in large part on the ability to look very deep into space using arrays. Right? And I'm going to just throw this out there. Anybody ever see the movie Contact with Jodie Foster? You have? All right, there's a scene in there where they have this large cluster of really parabolic antennas, but with huge gains, but there's, I don't know, 50 or 100 of them, and it's for deep space, really radio astronomy purposes. Do you remember that in that scene or not? It was in South America. That's the way radio astronomy literally is based on the ability to look very deep into space by having incredible gains from large arrays that are based on large dish antennas with incredible gains. So we've got this, spacing is that way. This is called the axis of the array. And it doesn't matter what the axis is. It can be X, it can be Y, it can be neither. Just has to be something where all these things are aligned on that. Now the first thing you do is we're going to have to assume we're a long way away from this array. So if you took the total length, which is d times n, and you would have to be r at much, much greater than d times n for this to work. But that's the way arrays work. Usually if you have an array antenna, like on a ship, you start looking at things hundreds of meters from that ship, all right, with that array antenna, not 50 feet from it. So that's the way it works. So now we're going to look at a distant point, but I'm going to, for the purposes of this lecture, I'm just going to show you, what I'm trying to do is show you parallel rays out there. This will be called R. It's going to a distant point. Can you all follow me on that? I'm not going to go ahead and make that point out there. You just got to imagine in your mind. All these are basically parallel and they land at the same point. Follow me on this, class? If you want to, you can put R is much, much greater than n times d. And I used to get a student, every once in a while, once every 5 years, I get somebody, well, what is much, much greater? In a way, that's a fair question. Maybe a factor of 100, but there is no hard rule on that. All right, if you're 100 times greater than n times d, which is usually trivial, you're usually much, much greater than that. So the next thing you have to realize is there's a distance, a slight distance difference between this ray right here. If this is, call it R, then this distance right here, if you call that phi, now, maybe I better not use phi. Dr. Wentworth does. I use phi for that. I'm going to call this angle right here theta. Y'all with me? Now just watch this part. This is the sort of the thing that determines what goes on. Y'all see if that's theta right there, then this distance here is going to be d cosine of theta. Y'all with me? Can you all see that? How many can see this right here? Right? It's just the projection of this, that you might say, the hypotenuse onto that axis. It's the cosine of that angle. That means that this vector r is r minus d cosine of theta. Oh, I said phi. I meant to say theta. And this is cosine of theta, right? And that means this is still r here. This is going to be r minus 2d cosine of theta, all the way down to r minus nd cosine of theta. Y'all follow me on that? So what I'm doing you now is showing you this small distance difference in all these radial vectors. That will come to play with a phase change, but not in a magnitude change of the fields. Do y'all agree with this? Give me a show of hands just to make sure you see it. Y'all see it? Okay. Now, think about it. There's a field way out here from this one, field from this one, field from this one, field from this one. They're all aligned in the same direction for all intents and purposes. We're in the far field. So I can say the total field, E total, will be equal to, and I get the field from the first one, which is just that right there. It's I naught, right? And I've said that there is no phasing on the first one, so it's I naught over K, or I'm sorry, over R, e to the minus j beta r. I'm going to drop the a theta there. I know everything's going to be in the a theta direction. Y'all follow me? Now I add the next field quantity. It's going to be plus I naught. This has a phase change. It's e to the j, and I used phi for that. Now here's the thing. I got to make a rational argument here. Do you all agree that 1 over a mile is about 1 over a mile plus an inch? You all follow my rationale? This is 1 over r. What is 1 over r plus 1/billionth of an r? About 1 over r. You all follow me? In magnitude, all right? When you take 1 over something that's very large and add something very small to that, it's about that 1 over something very large. So I can make that just r. Now I still have this business, e to the minus j beta, but now it's r minus d cosine of theta. Y'all see that? Because there, that r, remember it's e to the minus j beta r, there, that phase will have an effect. And I keep on adding. I can add another one, and I'll call that I naught, by the way. This is going to be I naught over r, e to the j 2 phi, and then it's going to be e to the minus j, and now this is going to be beta r minus 2d cosine of theta. And then I'll just dot, 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 all the way down to I naught over r, e to the j, and this is going to be n minus 1 phi, right, times e to the minus j r minus nd cosine of theta. And this is all in the a theta direction, but it's really meaningless to even put that down here. You're going to see why. Y'all with me on this? Yeah.
So does the last term lose the beta?
No, it doesn't. That's my thank you. Yeah, it's e to the minus j beta that r. But some of you are looking at this and you can see a lot of redundancy, right? You see the I naught appears in every term. You see the 1 over r appears in every term. If you look carefully, you all see that e to the minus j beta r appears in every term. Y'all with me? So all that stuff is going to get factored out. So I say E total is equal to I naught, and it's going to be over R right here. And then it's going to be e to the minus j beta r here. And if you look, then I have 1 plus e to the j times beta d cosine of theta plus phi, right there, plus e to the j 2 times beta d cosine of theta plus phi, plus, and it goes on out, e to the j, and this is going to be, I know there's an n minus 1 here. Actually,
Shouldn't the last one be n minus 1?
Yeah, there's, the thing about this is, if you look at this, there's 1, 2, 3, n total values there. But the first one really has an angle of 0, or I'm multiplying this e to the j phi by 0, where the summation starts at 0. I'll explain this in 1 second. When you get down at this, it's going to be e to the j, and this is going to be n times beta d times cosine of theta plus phi. I'm going to explain something to you. N here will be the number of elements. And when you do this, I'm just going to write the closed form of this solution, but I'm going to show you two things right now. Remember, this has got the a theta direction. This is in his book, but I want to just make mention of one thing here. You see this right here? That's the element pattern. Y'all follow me? I made that an isotropic element. You with me on this? I made the radiation. If you look here, the phase angle is in here, but the radiation pattern is isotropic. It's the element's individual pattern. Do y'all see that? This is called the element pattern. Just keep that in mind. This is the pattern due to the array. Now, the next part of the lecture just takes that equation and it fits it in a form that's easily manageable, okay? That's the second half. That's the reason I don't really need you to focus on that part. It's what I'm about to show you need to focus on. So when I take this, remember, this is the element pattern. And this has to do with what I termed the array pattern. Now, I want to speak to this right here, because here's where we do, I'm going to need this board to do it right. And if you're looking in the book, do you see where this is in Dr. Whitmer's book? Anybody looking at the book?
This specifically isn't.
Huh?
This isn't under arrays in his book. Like, not this specifically, because he does an example with 2.
No, he's got right there on page.
Because he uses the entire equation for, like, E fields, like the J, eta, DLI, like he does it for Hertzian dipoles.
If you look at his equation, oh, he doesn't use my pattern, he uses a short dipole pattern. This is equation 893. Oh, well. Oh, he's only got 2 there, sorry. No, this would be on
474 and 100.
Yeah, this is where it's showing a 474 on equation 8100. That's what basically I'm doing right there. All right, if you look at this, I'm going to show you the way, if you're an engineer, here's a tip. Anytime you can make a variable, equate it to something with a whole lot of variables in there that you're going to see repeated over and over again, do it. You all see how this e to the j, beta d cosine theta plus phi repeats itself over and over? So you create a new variable, call it that. Typically it's psi. Psi is equal to beta d cosine, I use theta, cosine theta, I think Whitworth uses phi, plus, or theta plus phi. Remember, this is the angle right there in Whitworth that's going to be associated with the angle of the array. And let me just tell you this. I'm really sort of regretting not doing it. If you look at his book, if you look at the on page 473, he uses phi where I use theta. That's a measurement from the axis of the array to the array vector. So let me repeat something. Matter of fact, what I'm going to do here, I hope you don't mind, just to be consistent with Whitworth's, I'm going to use this and then theta. And here, phi is defined if this is the array, like so, and this is the R vectors. This is D. this is phi. It's the angle the array makes with the R vector, so this is axis of the array. That way it'll be consistent with his book. In a lot of other books, they use basically what I use, but yeah.
So in the part like the element pattern, or no, in the array pattern where it should be cosine phi plus theta.
Yeah, I can do it right here, come on. And the only reason I'm doing this is to be consistent with his book. If you look at his book, you'll see what I'm talking about.
He actually uses alpha for phase.
Oh. All right. Why not use alpha? Well, then, so be it. Make it alpha. Actually, that's consistent with some other books too. So he's more right than me. But Greek letters to make him be okay. You all with me on this class? Anyway, this is a phase. So we have this. Now what I do is take this, and I'm going to rewrite it in terms of a summation. Just watch this. So I have E total is equal to, and I'm just going to replace that first term. I'm just going to call it E element. Now, the only thing that is the electric field from one element used in the array. All right, if it was a half-wave or a short dipole, it would be J eta times beta times L times I over 4 pi r. You with me with that, class? If it was a half-wave dipole, it would be J60I over R. All right? And it would be times e to the minus j beta r, where r would be the distance really from the first one, but it wouldn't matter. Y'all with me, class, on that one? So that's for the element. Now I multiply it by that array. And the way we write it is this. Because we're engineers and we like shorthand, so we write it, that summation as a compact little term. And what we do is say, we're going to go from n equals 0 to n minus 1 here. And now this term is going to be e to the j small n times psi. Now if you look at this for a second, you'll see how it works. The first term, n is 0, and that's 1, isn't it? E to the 0 is 1. Can you all see that? The next term, n is 1, it's e to the j psi. You see this? E to the j psi is beta d cosine phi. The next term is e to the j 2 psi. That's this term, all the way out to the end. You with me, class? Now, the truth is, I adjusted this. This, since my count goes from 0 to n minus 1, the last one is actually at n minus 1, not at n because I'm starting my count at 0. Follow me, class? I still have n elements. If you count from 0, 1, 2, 3, 4, blah, blah, n minus 1, you have n total elements. Follow me? All right. I have that, and this is where I take one moment and remind you about how many have me for signals and systems. And you know I like showing this. This is an old trick. I love math for one reason. It made my life easy when it came to a lot of geometric series and all sorts of Maclaurin series, different things like this. When you have the geometric series, and then you're going to see how this is a geometric series. It is. And when you had a series back when you took mathematics courses, and you had something where you had n equal from 0 to n, I'm just going to use n here, of a to the n, that equal to 1 plus a squared plus blah, 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 plus a to the n. You all remember that? Now, if I take the series and I multiply that whole series by a, this is still the same series, only I take a out in front. Y'all follow me? Just keep watching this. This is kind of neat. You actually did this. You may not have saw it done this way. Well, this is equal to 1. That's equal to a plus a squared plus a cubed plus dot 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 a to the n plus 1, isn't it?
I want you to convince yourself of that.
I took the top series and I multiplied by a, right? Every term just is multiplied by a. So the 1 has a, the a is a squared. Y'all follow me? Now the final thing is I subtract. All right? I subtract this from that. Now what do I get? I get a 1, don't I? There's nothing subtracting a 1 out. I get 1 minus, notice, a subtracts that away. A squared subtracts that, a cubed. All the way out, a to the n subtracts a to the n, but you're left with a to the n minus 1 with a negative sign. Or n plus 1. Y'all with me? So what did I actually do? I took I'm sorry, I took 1 minus a, right? And I took it times that infinite series. And I found out when I do that, because this is the same thing I'm doing over there mathematically, isn't it, class? I found out that I get what? I simply get, well, I didn't write the whole thing down there. For this, right here, I get this. So I simply get 1 minus a to the n plus 1. Do you all see that, class? Right? Can you see it in the back there? All right, now, why did I do it that way? Because if I take 1 minus a over here, now I have what that series converges to, and it doesn't matter what the value of a is or what the value of n is. Capital N. Y'all with me on that? How many remember that? Kind of, sort of? This, didn't you have, you had series stuff in math, right? You had geometric series, Maclaurin series, Taylor series. The real thing is, what do they converge to? Because nobody sits there and adds this stuff. Does anybody know how this came, or how some of this stuff was developed? Anybody? There's a famous guy named Gauss. You've heard of Gauss. Gauss is brilliant. And Gauss was, I was told this, it was in a math book I had. And I had it when I was in 3rd grade, and I'll never forget this. We were always given assignments to do stupid stuff, like write the ABCs backwards or something. All right, the entire alphabet backwards and then forwards and backwards. Well, the reason we were given those assignments is they wanted to grade during class, and so they didn't have to take stuff homework. One of the things they do is say, I want you to add up all the numbers from, say, 1 to 100. That takes about 10 to 15 minutes for most kids. Gauss had none of that garbage. He said, well, if you had 1 plus 2 plus 3 plus plus 100, that's interesting, but if you write that series backwards, it's 100 plus 99 plus 98 plus really 1 here, right? Ah, and if you add these two series, you get 100 101s. But that's twice the number, so you divide by 2. And Gauss came up in about a minute with that. And the teacher was, how did you get it? You must have cheated, Jeff. There it is. And that's when the teacher took Gauss to some professor, and the rest is history. That's the truth. But that's one of those guys who was born with a genius, but it was made manifest because he didn't want to just do stupid stuff. And that's true with engineers. They don't want to do repetitive things that are stupid. You want to find a clever way to do that, and that's this right here. I'm not going to add every one of those terms every time I'm going to write that equation. This equation is trivial. Got it? So that's how it came about. It's an interesting story. I always love that. And that's why Gauss is my personal hero when it comes to electromagnetics. Now, over here, we're still not done. Now I'm going to go ahead and take this right here, and I'm going to show you what we got. We have this, right? So we have a summation of e to the j, and I used n psi from n equals 0, right, to n minus 1. right? Well, if we allow A to be equal to e to the j psi, then really what I have up here is a summation from n equals 0 to n minus 1 of A to the n, don't I? Take a good look, convince yourself of this, because this part is important. Y'all agree with me there? And here you have the closed form. So that equals 1 minus A, or e to the j, right? J psi. And it's times n plus 1, but the summation goes to n minus 1, so it's just n. Y'all follow me on that? The summation ended up at n minus 1. We know the series math says that you actually go to n plus 1, where n is the end of the series, right? And then you divide it by simply 1 minus e to the j psi. Y'all with me? So that's that whole series. Doesn't matter how many elements. But that's still not really helpful for a couple reasons. How many see that thing you can't look at and tell what's going on? Right? Everybody should say, yeah, I don't know what in the world's going on. If psi is equal to 0, then I got 1 minus 1. It's 0 over 0. I've got to use L'Hopital's rule to figure it out. I don't have a good feel for that. So what we do is always try to get things into trig functions whenever possible. Now, to get it into a trig function, I've done this for a long time. I immediately see I get a minus sign. And this e to the j crap that appears at the top and the bottom, I know I can probably fit this into a sign. So I ask myself, what do I need to do? Well, I need to have the angle here, whatever the angle is here, e to the j whatever, it has to be e to the minus j whatever here. Y'all with me? So what I'll do is this. I'm going to factor out, you'll see this in a second, e to the j n psi over 2 out of this one here. And when I do, I have e to the minus j n psi over 2 here. And then I have e to the j, and this is going to be n psi over 2 here. Take a look. Y'all with me? There's nothing tricky here. I'm just trying to fit the form of a sign. Oh, by the way, if you don't know it, e to the j theta minus e to the minus j theta over 2j is the sine of theta, right? So if I multiply this by 2j, now I have what I've got there. Y'all see it? All right, so coming back here, that's the top part. The bottom part here, I factor out e to the minus, no, I'm sorry, e to the plus j psi over 2. And I get e to the minus j psi over 2 minus e to the plus j psi over 2. Agreed? You'll see this in Whitmer's book, but I want to show you how he got it. He just puts it there. You with me? Now, once you get to that point, here's what happens. This top one, I'm going to pull a minus sign out in front. And then I'm going to switch these terms. Do y'all follow me on that? So when I pull a minus sign out, this becomes plus, and that becomes minus. Then with the bottom one, I'm going to pull a minus sign out. That becomes plus, that becomes minus. You got me? Now I did that so you see this. Because what is this right here? Look over there. The minuses cancel, and I have what? E to the j n psi over 2 over e to the j psi over 2. And then it's times what? That becomes 2j times the sine of n psi over 2, right? And the bottom one is 2j times the sine of psi over 2. Take a look at that just for a second. Do you agree with that? Now, I didn't put I mean, I'm gonna get rid of those two J's, but I want you to just notice, this is what I did, didn't I? I let the angle be what? Inside over 2 up top, and down below, the angle is psi over 2. You all see it? Take a look. Right? How many see this right here? You're looking squinting at me, I'm wondering, what don't you see, my writing or the?
No, I'm just wondering how whenever you change the sign of the EJ in psi over 2, how did that change the exponential sign?
No, when you pull out a negative, right, you switch, this one comes up front, this one goes in the back.
Oh, okay,
So
okay.
that, instead of just erasing and rewriting, it,
Okay, that
that's
was
all I
like
did.
completely throwing me for a loop.
Y'all fun? Everybody with me on that? That's a good question. Okay, now, at that point, does everybody see the two J's or is that, right? Y'all with me on that? So, I'm just gonna get rid of them. Next, is there a better way to write this? If I take this angle upstairs, isn't that e to the minus j psi over 2? So I could actually make that j n minus 1 psi over 2 up top, couldn't I? And by the way, that's only a phase term, so I really don't care about it. Okay, and guess what? This right here is the array factor, but this is for the element multiplier. This multiplies the E field. So just write this element, or I'm going to call it F, and then I'm going to put array, but I'm going to dash it with an E. So you know this is the thing that multiplies the E field. Understand? It doesn't multiply the power pattern. Y'all with me? So now let me give you an example of what actually happens. Now, this is a compact formula, isn't it? Psi is beta d cosine of the angle, right? Phi plus the phase, the progressive phase. This only works for antenna arrays where you have, by the way, very common. This is a very common method of beam steering, where you have a progressive change in the phase. It's the same amount of phase change between all elements, same magnitude current. I want to make mention of that same magnitude current. That's the tricky part. Here's why. These antennas are close. And there is an impedance. When you drive an antenna, it's not just the impedance of that element, if it was in just free space. The other elements have a parasitic effect on that. They influence it. So the driving point of the impedance of the antenna in the center is different than the one on the end. So you can't just assume if I use the same voltages, I get the same current. Y'all follow me on this? So they have things called power couplers that guarantee the same amount of power, really current, goes to each one of those antenna elements. All right, and that becomes, that they have to be controlled electronically or else it won't work. But I'm saying this for your own benefit, because a very common mistake that Dr. Riggs can tell you all about, if you ever have him for something, is when some guy, an engineer, goes out there and he knows he wants the same current in some short array. Maybe he has 10 elements. So I'll just use a given voltage, and I'll have a phase delay for each element if I want to steer the beam. And the array pattern is nowhere near what it should be. The reason is the center elements will have an impedance maybe 2 times what the outer ones will. And it gets completely different currents. That's the reason. Yeah.
I just had a question at the end. What does it say on the bottom, like naming the bubble?
Oh, this?
Array.
I just called it F array dash E. It's for, this is what multiplies the E field, the element, the pattern for the E field. I'm going to give you an example. And I got to tell you one other thing too. Almost all arrays that I know of, just about, have the same exact spacing between elements. Doesn't have to be. Almost all. The thing that changes is there's tapered currents. They want the end ones to have less current than the middle ones for a lot of reasons. And they have, so they're going to have a change in the magnitude of the current, but the beam steering will still be done the same way as this. And that's advanced. So now we get down to an actual example. And this is one that would make, I'm going to just tell you that I'll get to the power in 1 second. If I have antenna elements like this that are short dipoles, and say I have 3 of them. They're oriented in the vertical direction. The array is this way, so they're perpendicular to the array. You with me, everyone? They're short dipoles. They're going to have currents I naught e to the j phi, I naught e to the j 2 phi. All right, on there. The spacing is going to be d, and d will be in terms of wavelengths. So I'm going to make this lambda over 4 just to show you how it works. Now, I know that the angle that measures the actual phi is from a radius vector to the axis, and this is the axis of array, right? Y'all with me on this, class? This is important when I'm showing you, because there's mistakes made here all the time. When I look at the way this thing's oriented, the actual angle I want for my dipole equation is this angle, isn't it? Isn't it always the angle from the axis of the antenna to the radius vector? Now that angle is equal to 90 degrees minus phi, isn't it? Can you all follow me on this? Very important you see this. In other words, angle is not angle. Phi is not theta. It could be if I took these antennas and shifted them along the axis, right? Then the angle would be the same. Do you all see that? If I just took these antennas and rotated them by 90 degrees, then phi would become theta. But in this case, it's not. You all got that? How many can see that? Really important that you see that. Now, when I look at the total E field from that, first I get the E field from the element. That would be J eta beta I naught over 4 pi r, right, times e to the minus j beta r. That is nothing more than the E field from a single short dipole. I'm going to put the sign here in a second. Don't worry about that.
You meant length. Length.
Excuse
Are we
me?
assuming a length of 1?
What? This is for the element, I'm sorry, yeah, times L. You're right, times the sine, you're absolutely right. Sine of theta in the A theta direction. That's the element pattern, right? Now you multiply it by the effects of the array. And n minus 1 is 2, so then I have this whole thing, and I multiply it by e to the j 2, and this would be sine, I'm going to leave it as sine over 2, so it's just 2 sine, right? And then it's times the sine of n psi over 2, or 3/2 psi, over sine of psi over 2, where psi would be equal to beta d. And I'm going to put it down like this first, times the cosine of phi plus phi. I didn't even put a phase shift on there. But I know that the separation I made equal to lambda over 4. So beta is 2 pi radians, 2 pi over lambda, times lambda over 4, or divided by 4, times the cosine of phi plus alpha, or if psi is equal to pi over 2 cosine of phi plus alpha. So that would be the cosine. You all see it? Okay? Now, the next logical question is, how do you get an antenna pattern for this? Right? Some of this you do graphically, I'm going to level with you. But here's how you always get the nulls. And I'll show you how to get the peaks in a second, but when you want to get the nulls, the first thing you look for is the nulls in the element. A null is a 0. Where is it 0 here? When theta is 0 or 180 degrees, right? So we know we have a 0 in this direction, and we have a 0 in this direction, right? We have a relative maximum in that direction, don't we, for each element? Now we look at the array, and this is where it gets a little, this gets a little more, a little trickier. When I look at this, well, that's a sine over a sine, right? Now, here's the thing, if the number of elements is large, this looks just like a sinc function. Y'all remember sinc? And a sinc function, remember the sinc was sine x over x? When you look at this, it will have a 0. Remember, a sinc function has a maximum when the argument of the sinc is 0, right? Technically, it's sine x over x. This one will have a peak value when the value of psi is 0. Just listen to me, all right? Okay? When psi is 0, this magnitude, you gotta use L'Hopital's rule for this, the magnitude will be 3. The magnitude will always be the number n for a maximum value. You all follow me on that? Now the power would be n squared. I know it's gonna be, the maximum will be where psi is 0. Do you all hear me on that? Psi is 0 doesn't mean anything in terms of the angle. What do you have to do to figure that angle out? You make this 0 is equal to, for the spacing I gave you, pi over 2 times the cosine of phi, or you make minus alpha equal to that. You all follow me? Normally it would be plus alpha, right? Because this is equal to 0 for the maximum, isn't it, class? I just want to make this last point. You with me on that? So if this is 0, I can take this to the other side. This angle is where there will be a maximum for the arrays effect, right? Now, if this was 0, just take a look for a second. I'm going to say, suppose there is no phase shift, and I make this 0. Well, that means pi over 2, I can get rid of it. I have cosine of phi equals 0. When is the cosine of phi 0, class? 90 degrees, and this is something I want you to listen to and hear me. If you had no phase change, and you were just talking about the effects of an array, the maximum will always be broadside. Now just listen to me on this one. There can be no phase difference for any of the signals from these things that they're going straight out from that array this way. Y'all follow me? And what happens as you beam steer, you change this phase so that 0 shifts. And you can steer the maximum of that beam all the way around from the North Pole to the South very easily using electronics. That's called beam steering, and you can do it extremely fast. Hundreds, thousands, even millions of times per second if you need to. And that's called beam steering, and that's why electronic arrays are so much better than these. You've seen these parabolic dishes on old ships that just rotate, their legacy radars from World War II? Well, they're cheap, but they can't scan an area real quick. And if you're tracking 5 different planes, it's almost impossible to do with that. But with electronic arrays, they can quickly jump from one plane's position to another and see the small change in position, as well as they can search the area at the same time. Now, I'll get more into that later. I am out of time, but did you all follow me as far as the thought process to get the final form? I'm going to put that form down. In the notes, I'm going to give you problems, and I'm going to say to get the power, hear me now, the power's trivial. You know why? You ignore the phase, you take that term right there, which I call the F array there, and you square the magnitude. And then you multiply it by the power pattern from a single element. And that's what Whitworth does in his book. He doesn't even bother with E-field like I'm doing. But I'll get to that, and I'll put them on one note. And then for Friday,